Hi, my name is Salase Dumenu and my partner is Andres Cordova. This is our presentation 3 for ENGI 460 and we will be discussing uniform random numbers. Okay, so we're going to look at a quick overview. We're going to be discussing linear congruential generators. We're going to look at two kinds of those, which will be the mixed linear congruential generators and the multiplicative linear congruential generators. And then we're going to talk about the theoretical test for random numbers and then some problems with increasing dimensions. Alright, so what are linear congruential generators? They basically deliver a sequence of non-negative integers using the equation provided below, and then the recurrence uses four parameters that are usually set by the user, and then the four parameters involved are a multiplier, which has to be greater than 0, a seed, which has to be greater or equal to 0, an increment, which is represented by c, which has to be greater or equal to 0, and then a modulus, which has to be greater than 0. Now this is just an equation right here, so you see your x subscript I is equal to a, your multiplier, times your c, I minus 1, which is indicating that whatever number you have there, minus 1, plus c, which is the increment, mod m, the modulus. And as you can see, for your I is 1 to infinity, basically. It could be anything from 1 to infinity. So we're going to go into MATLAB to see an example of how this works and then how the LCG basically generates the numbers. And that will be in the next slide. So in MATLAB, we're going to run the code, but first I'm going to go over it and then basically just try and explain what the code is doing. So as you can see, my four parameters here, this is my seed, which I'm choosing the number 3. My multiplier for this problem will be 9. The increments of 3 again, and then my modulus is 2 raised to the power 4. And then what I'm going to, that is going to be put in a loop for I equals 1 to 18. This can be any number. We're just running from 1 to 18. And then the equation here is that x parentheses I plus 1 is equal to the mod of my multiplier times my seed plus 3, with taking that is all multiplied by my modulus of 2 raised to the power 4. And then after that I end it, and I want to know what x is, and then the r is going to be equal to my x divided by my modulus. And then I'm going to go ahead and then get a plot of r and then see what the histogram looks like as well. So I'm going to go ahead and run this code, and then we're going to see what the numbers look like. Okay, so I'm going to scroll up. That's our plot and histogram, but come back to that. I want to try and talk about the numbers here. So if you look at this, you see that it's generated numbers here, but one thing we need to pay attention to is that we need to be able to tell when the sequence ends. And then if you look at it, it starts from a 3 and then goes all the way down 0, and then the next number is 3. And to avoid repetition, we have to be able to tell where the sequence ends. And then whenever it generates a number, the number started with, whenever it generates the same number, that's when you know that whatever comes after that is basically going to be a repetition, and you want to avoid those kind of things. So over here, if you look here, you see that column, the first number is 3, and I believe if we go down, it should be number 16 or 17 if I'm not wrong. And that is what is giving us 17. The 17th number here is also 3. If we go down to our r, that means that whatever our first number is here, which is 1.85, should be the same one at the bottom. And as you can see right here, 17th number right here is 1.875 as well. So that helps us tell when to stop sequence, in order to prevent unnecessary repetition. Alright, so the next one we're going to look at is the mixed linear congruential generators. And then this is basically a kind of a linear congruential generator where it uses basically the same parameters, but for this one the increment is expected to be greater than 0. So, and that is basically the major difference. So to make sure that this runs accurately, it is good to have a modulus which is very high. So basically I guess the general rule of thumb is to go with the maximum number of bits used to represent positive integers with a particular computer or any language combination. So if you have a 32-bit, you're basically going to run your code with your m equal to 2 exponent 31, because you know that 32 you have to subtract m minus 1 to run that. And that is basically the main difference here. I have code for this, and I'm going to go into MATLAB and run that as well, so we see what the numbers look like when we use this approach. Okay, so this is the code that I generated for the mixed linear congruential generator. It's basically very similar to the linear congruential generator code, but we're going to just run through this as well. And then, so you see that we have a reasonably high C, and then our multiplier is also very high. Our increment is 1, it's equal to 1. And then our modulus, like I said in the slide before, we're going to use 2 raised to the power 31. And that's going to run for basically 5 iterations. So from 1 to 5, this is the same equation as before. Just now you see that instead of our 3, like for the linear one, we have a 1 here. And then our modulus. And then we want to find what our R values for that are going to be. And the main reason why we choose a high modulus is because we want to ensure that the generator has a full period when C is chosen to be R value, because that is one of the conditions we have to satisfy. So I'm going to run this. When I run this, it says a lot of values because it basically runs, I'm assuming it runs the first one, the first 2, and then as you can see, as it goes to every R, see that it went from 3 numbers, 3 to 4 numbers, and then the final one is 4 to 5 numbers. And the next one is the multiplicative linear congruential generator. That is also another branch of the LCG, but this one assumes that your increment is equal to 0. So basically, for this one, there is no increment, and that is why the formula now changes to just your multiplier times your C, I minus 1, mod M. And I just repeated the 4 parameters, but just showing that the emphasis is here. That C is equal to 0 in order for this case to hold. Now there are 2 constraints or conditions that usually must be met for the maximum period prime modulus generator, and that is that M is prime and then the multiplier is a primitive root of the modulus. So now we're going to look at the theoretical test for random numbers. And we know that LCGs usually follow one of these 3 types, where type 1 is a full period multiplicative where lambda is equal to M. Type 2 is the maximum period multiplicative prime modulus, where lambda is equal to M minus 1. And type 3 is the maximum period multiplicative, where lambda is equal to M over 4. And usually when you run these, you notice that the outputs for type 3 generators is basically identical to the corresponding output of a type 1 generator. So the theoretical test basically uses the values of your A, C, and M, which are your multiplier, your increment, and your modulus respectively, to assess the quality of the output of the generator over the entire period. And that is basically what the theoretical test is all about. Alright, so lastly, we're going to look at problems with increasing dimensions. And then, with increasing dimensions, the functions of a random vector are approximates to be discrete, rather than the desired continuous. And then also, based on an average distance to a neighbor, graininess of discrete approximations can be a problem when you increase your dimensions. And then lastly, sufficiently large moduluses tend to ignore the graininess of a sequence.